Alright, we're taking a look at the first use of the nabla operator called the gradient. And so remember we discussed the gradient takes a scalar valued function and it gives us a vector, a vector formula, a vector equation. So the del operator times the scalar function f of x and y, which I have drawn here. I chose a paraboloid because they're kind of fun to work with and they're easier to draw. So f of x and y is going to be the paraboloid x squared plus y squared. You could think of f of x and y as a direction of its own, or you could consider it equal to z. And you'll see this kind of gets a little bit confusing the further we dive into these sorts of operations. Is it f of x, y? Is it z? Well, in this case, they're interchangeable. So I'm going to call this the f of x, y axis or the z-axis. It really doesn't matter. It's some output plane for the scalar function. But the only inputs for the scalar function are x and y. And then they'll give you a scalar output. Alright, so we take the gradient by taking the partial derivative of the scalar function with respect to x, the partial derivative of the scalar function with respect to y. And when we do that, the partial derivative of x squared plus y squared with respect to x is just 2x. And likewise, with respect to y, we get 2y. So this is our gradient. This is our gradient function for this scalar function. Well, what does it tell us? Okay, so let's pick a point and see if we can kind of figure out what's going on here. I picked point 2,1. You can pick any point. And the gradient of f evaluated at the ordered pair 2, 1 in the xy plane, it outputs a vector that's also in the xy plane that has an x component of 4 and a y component of 1. So here's the point we chose, the ordered pair 2, 1, and here's the vector that came from it. So one thing that you may notice is that it's kind of pointing in an interesting direction, but maybe let's pick another point. See if our sneaking suspicion is true or not. So let's go ahead and pick. Let's say we pick this point over here. So let's evaluate at point 2, which I chose to be. Now it's 0 on the x-axis, 2 on the y. And so let's evaluate the gradient of this scalar function at the point 0, 2. That's going to give us 0 in the x for our vector, and 2 times 2 is 4. So now we have a vector pointing 0 in the x direction and 4 in the y. So at point 2, we're pointing 0 in the x direction and 4 in the y. So now this is 4 long and there's no x component. And so the interesting thing there that you may have noticed is that they all seem to be pointing away from the origin. And in fact, if you mapped out the two-dimensional gradient function, you would find that they're all centered about the origin. And you may wonder if all gradient functions are centered about the origin, and they're not. Only ones where the minima is at the origin will the gradient function be centered about the origin. And the reason why that is because the gradient, when evaluating a three-dimensional figure on a 2D plane, the gradient of the function points in the direction of largest increase of height. So in other words, what this is telling you, it's telling you if you were at the point above the point that you evaluated on the graph, so in other words, we're here on this scalar graph, and we wanted to know which direction we should travel in to get the greatest increase in height. We would follow the gradient projection. So in other words, if we would want to travel along this line in order to get the steepest increase in height for this scalar function. And indeed, it's true with all of these arrows. They're all pointing in the direction of largest increase. And you'll notice something else. They're smaller near the origin and get bigger as you get further out. And that makes sense because a paraboloid isn't linear, right? It starts with very small slope and then it really increases. It never goes to any asymptote, but these arrows will keep getting bigger the further and further out you go. And so that's the interpretation of the two-dimensional gradient. Another fun fact is if you were to draw a curve, so I'm going to pick a curve, I'm going to dissect. I'm going to dissect this paraboloid along parallel to the xy plane and get a curve. So this curve is parallel with the xy plane. And if we wanted to know the normal vector for this curve, you remember we were talking about normal vectors for vector curves like lines, the r of t. You could treat this as an r of t, this curve that's on top of the paraboloid. And if you picked the projection of where the point is that you're at, the direction of the gradient would give you a normal vector to this curve. And so what we have here is a tool for normality. It's going to help us find normals to the surface in the next example. Here it's giving us normals to curves of surfaces, and it also points in the direction of greatest incline. Here's another example with the same curve. Okay, so, well, heck, let's see how little I can erase. I'm going to get rid of all this, and this time what we're going to do is we're going to do something that seems kind of tricky and maybe a little trivial. But what we're going to do is we're going to say, well, if f of xy equals x squared plus y squared, and f of xy is also equivalent to z, so z equals x squared plus y squared, what's to keep us from subtracting z over here? Now you may think, well, this is 0 here now. Let's do a trick here. Let's say instead of that being 0, let's say now instead of a function of x and y, we have a function of x, y, and z. And this is fascinating. So now we've essentially, we've pumped ourselves up into a different dimension. We started with a kind of in a 3D coordinate system, but with a 2D gradient, okay? Now we're going to be in a 4D coordinate system, and we're going to have a 3D gradient. Now I want you to think about it this way. If we considered this to be x, if we considered this to be z, and now z is over here, now we have 3 input spaces to 1 output space. So that gives us 4 dimensions. Now if the 3-dimensional graph gave us a 2-dimensional gradient, then the 4-dimensional graph is going to give us a 3-dimensional gradient. And so what we're going to do here is we're going to take the del operator of our new graph that we call f of x, y, and z. And so to do that, we have to take the partial with respect to x. So the partial of the function with respect to x, partial of the function with respect to y, and the partial of the scalar function with respect to z. And when we do that, we'll get our gradient curve for this function. df dx, that's 2x. df dy, that's 2y. And z is just minus z, so we're just going to get a minus 1 here. Well, now what we're going to do, so now that we have a 3D gradient, this is no longer our gradient in the xy plane. That's our 2-dimensional gradient for this function. Now we're going to take a look at the 3-dimensional gradient. Let me just make some room. Alright, so let's get rid of this normal. Draw a few more hidden lines. That looks good. Alright, so let's pick a point. And this time, let's pick a point that's actually on the curve. Okay, so let's pick an x and a y point. So we'll say that our x, y, let's make it 2, 1. When we plug in 2 and 1 here, we get 4, right? Well, yeah. Okay, so 2 for the x, we get 4, plus 1 for the y, we get 1. Therefore, z, to be on this scalar graph, has to be 5. So for the ordered triple 2, 1, 5, let's say that's 2 in the x. Let's make our scale a little smaller. 2 in the x, 1 in the y, and 5 in the z. So now we're hanging out on the surface of the scalar curve itself. And we want to figure out what our gradient represents there. So we go ahead and plug in our values, and we're going to figure out the gradient. So in other words, the gradient of f of x, y, and z, and we're going to evaluate it for the point, the ordered triple 2, 1, 5. And so if x is 2, 2 times 2 is 4. If y is 1, 2 times 1 is 2. And nothing times, or negative 1 times negative, or I'm sorry, because there's no z in here, it just stays negative 1. So now we have a vector in 3 dimensions. Let's go to the point and draw it. So we have 4 in the x. We've got 4 in the x. Then we have 2 in the y. And then we have negative 1 in the z. And this might be kind of difficult to see because of the way I drew it. And it's not that good of a piece of art. But this vector that we got at this point is an arrow that just so happens to be normal to the surface in both the x and y direction. So if we're looking to find a normal vector to a surface, remember when we did a gradient in 2 dimensions, it showed us a normal to the curve. Now in the 3 dimensions gradient, it's showing us a true normal to the surface. And so this is actually a normal vector. It may not be a unit vector yet, but what we've learned now is that if we want to find a normal vector to the surface of a curve, we turn the equation into a 4-dimensional equation, 3 dimensions of input, 1 dimension of output, and we take the gradient. So the gradient of that function is now going to be normal to your surface. And if we want to make it of length 1, if we want to make it a unit normal vector, we will divide by the magnitude of the gradient. So this is called a normal vector to a surface. And I like to use a little n as opposed to the big N, because the big N is already used for parameterized curves. So this is the gradient. It's pretty fascinating that we can pump a function into a 4th dimension and then learn 3D truths about it using this function. So I hope you enjoyed this, and I'll see you next time for divergence.